I'm almost done with 12. I should be done with that today. If I can get everything else off my desk, that'd be great. Okay, any questions from last time before we get started? Okay, so the last thing we did is we talked about these notions of degree and order for a power series. Let me start with this proposition that I won't really formally prove. I'll talk through it a little bit. R is commutative. Respectively has identity or is a domain if and only if Rx has identity or is a domain. And the same holds, or the same is true if we replace Rx with power. Okay, so let me point out that just by the definition of multiplication for the power series ring, then it's clear that it's commutative, right? If R is commutative, then the power series ring is commutative just by our notion of multiplication, and so the polynomial will follow from that as a subring. The interesting part probably is domain. So note for domain, if R has an identity, then so does Rx, and our power X is the same identity. No problem there. And if f of x, g of x equals 0, well, actually, let me put it to you this way. If f of x, g of x are non-zero, and R is a domain, then degree of f of x, g of x is degree of f of x, is degree of g of x. This formula here holds for R as an integral domain. So f of x, g of x is 0. And of course, all you have to, I mean, you could do this sort of more primitively just by writing f of x, just writing what it is and writing what g of x is, and noticing that when you multiply these out, the leading terms, and they multiply together, give you a non-zero leading term. Okay. Let's see here. Here's an interesting. One of the important pieces often in commutative algebra is trying to tell when you have how the units relate to each other. So suppose R is a commutative ring with identity. Number A, f of x, a polynomial, is a unit in Rx if and only if the constant term is a unit and all other coefficients are nilpotent. So the constant term has to be a unit in R, coefficients are nilpotent.
Does that just mean nilpotent in R?
Yes,
Okay.
nilpotent in R. B, is unit. It only is. This is kind of cool. For power series, you only need the constant term be a unit. That's all you need. Notice that this is different than the condition here. In fact, by the way, this means, for example, let me point out, if R is a domain, well, what does it mean for a polynomial in a domain to be a unit? Well, you have to have the constant term of the unit and all other coefficients are nilpotent. But in a domain, the only nilpotents are 0. So in this case, U of R coincides with the units. This. So for example, the polynomial 1 plus x, not a unit here. Not surprising, right? 1 over 1 plus x is not a polynomial. However, it is a unit here. Because, I mean, if you've ever taught Calc 2, 1 over 1 plus x, 1 minus x plus x squared minus x cubed, etc. And C, E of x and R power x is, well, let me just, so I don't have to get into all this thing here. Let me just say that this is a domain. G of x and R power x is irreducible. Yeah. G of 0 is irreducible. So that's kind of nifty that you can tell the irreducibles. Well, no, I shouldn't say that, but if the leading or if the constant term is irreducible, then the whole power series is. Let me at least outline some of this. Oh, actually, let me give you an example first. In Z6, 0 is only nilpotent. So U of Z6 is equal to U of But let me point out that weird things can happen because if you look at 2 bar x plus 3 bar, 3 bar x plus 2 bar, this will flat make you angry, right? Degree 1, linear polynomial is degree 1, degree 2. You get 6 bar x squared. 4 and 9 is plus 13 bar x plus 6 bar. This is 0 and this is 0 and this is x. Right, so there's an interesting factorization of just monomial x. And of course, by illustrating one more example, what's this business with nilpotents? Why do nilpotents work? Well, here's the deal. If you have like actually, let's make this more dramatic. Let's look at Z16 backs. This is actually a nilpotent. So this should be, or this is a nilpotent, so this should be a unit. And how do you do it? Well, you do the old von Neumann trick here. notice that if I continue the pattern here, I'll have higher and higher powers of 2, which is all 0 from here on out. And if you multiply this out, you get 1 bar, and then you get 2x, well, you get 2x minus 2x, then you get 4x squared minus 4x squared, and then you get minus 8x squared plus minus 8x plus 8x cubed, and then from the last term you get is 16, which is 0, so you get that. And that's essentially why I'll let you puzzle out the proof of a for the integral domain case. This is easy because it's just a degree argument. But see if you can generalize this example to nilpotence. For the B part of this about the power series, I think that this is really an interesting thing. I give a more complete proof in the notes, but I'm going to give you a sloppy proof because it gives kind of the idea. This direction is clear, and the reason it's clear is if this is a unit, that means that you have to multiply the series by some other series and get 1, which means the constant terms have to multiply together to be 1, which means the constant term must be a unit. The interesting part, of course, about this is that is all you need. That is to say, all you need is a unit at the beginning, and you're good to go. Let me point out, well, let me do a sketch that I think paints a good picture. Suppose you have u plus a1x, say 2x squared forever. Let me point out that I can write this as u times 1 plus b1x b2x squared forever. Just by pulling, and now I can pull a unit out of everything. So b1 is like, b1 is the same thing as a1u inverse, and b2 is a2u inverse. But let me point out that to show that this is a unit, it's equivalent to show that this thing here is a unit. Because if I can invert this, then all I have to do is multiply by u inverse, and I'm good to go. So without loss of generality, I'll assume my power series begins with 1. Right? So here's my sloppy high school thing here. One, two. Actually, I gotta divide that into 1, don't I? Now, basically, I have to show that this quotient, when I divide this into this, always works. Well, 1 goes in this many times. And then subtract. Now, notice 1 goes here. And let's see, this is minus b1x minus b1 squared x squared minus b1 b2 x cubed minus b1 b3 x4, etc. And you subtract again, and this gets worse because when you subtract here, these are dead, and you get b1 squared minus b2 squared. And then b1, b2 minus b3, x cubed, etc. But notice that you keep being able to divide in because all you have to do to keep this going is to be able to multiply 1 by something to get this. And this is always the case because it's 1, right? So for example, the next term that I should get, assuming I put all this right, is b1 squared minus b2, right, x squared. And then I'll get a new mass, but 1 has to divide into it. Because this is a power series, I never have to stop. And so that's the quotient. This is why this always worked when, and all you need is a unit here, it's because you never have to stop. The more formal proof, the way the more formal proof would do is show you can start it, and then assume inductively that you've built sort of the nth one of these, and then show that you can build the n plus one. That's basically the general strategy. And finally, number C, show that g of x is irreducible if g of 0 is a unit. That follows from the previous. Suppose g of 0 well, notice that if g of x is h of x, k of x, then g of 0 equals h of 0, k of 0. But this is pi, which is irreducible. Therefore, h of 0 or k of 0 is a unit. Therefore, h of x or k of x is a unit. So, g of x is irreducible. Any questions on that? Let me point out, we did talk about factorization earlier. There's different things that can happen. Let me give you some examples so we compare some stuff that happen. Let me point out, first of all, for number C, that this is not an if and only if. It is true that if the constant term is irreducible, then the whole power series is irreducible. But the converse does not have to be true. If you look at 4 of x, this is irreducible. And z power x. Because I only have to take this a little ways to see. If it's not irreducible, it has to break down into two power series that look like this up to a sign. Because the only way that you can factor 4 is 2 times 2 or 1 times 4. If you take the 1 times 4 option, then one of those two is a unit, right? And so you haven't done anything. So the only non-trivial way you can do this is this way. But notice if you multiply this back, you get 4 plus 2 times A1 plus B1. And then, and this is a contradiction. Because the coefficient of x has to be 1. Right? So 4 plus x is irreducible, even though its constant term is not irreducible. On the other hand, and this is kind of weird compared to, notice of course 4 plus x is an irreducible polynomial as an element of zx, right? Because it's of degree 1. Contrast this is irreducible in zx because it's a polynomial of degree 1. You can't break it down any further. But this is kind of fun. I'll just start us off. Now I can do this. So let's play the math game here. This is 6 plus 2b1 plus 3a1 x. And I can force this to be 1. Can anybody tell me? I mean, there's actually infinitely many ways I can do it, but how do I know that I can solve that equation? 2b1 plus 3 A1 is equal to 1.
Because the greatest common divisor is 1.
That's exactly right. The greatest common divisor of 2 and 3 is 1. So I can think B1 and A1 sagaciously. So it's 1. So let's assume that I've done this. Now let's try to build the next one. A2 x squared plus B2 x squared. And now the next term I get is bigger. So I get, well, let's see what I get. I get A1, B1. That's just some number that I've got because I've already chosen A1 plus B1. And then I get plus 2 A2. I'm sorry, there's 2 B2 plus 3 A2. And I have to have this be minus A1 B1 because remember, I want the whole thing, I've got a 0 term right here. But again, I can do this because the greatest common divisor of 2 and 3 is 1. And so basically, there's a linear combination of 2 and 3 that can be any integer I want. I'll pick it to be this. And now I've got these established. And now just continue the process. And so actually, this thing is not an irreducible. It breaks down into 2 non-trivial power series. And sometimes things work sort of the other way. Part C of the previous theorem is not true for polynomials because no has a power series f of x, which is x squared plus 3x plus 2 is irreducible. Because 2 in z because the 2 is irreducible there, but it's also equal to 2 plus x, 1 plus x, so reducible in dx. And see that irreducible factor in the polynomial ring is undetectable in the power series ring as a unit. Okay, any questions on that? Any questions? Okay, so now that we've kind of talked a little bit about the units and the factorization properties, a little bit of polynomials and power series, let's talk a little bit about the interplay because we're going to build up to some more sophisticated theorems about their behavior. So proposition 566. What are in community 1 and I and R an ideal? Before I start this theorem, let me make a couple of definitions. You've seen this in the homework. What do I mean by IX? I think the notation is suggestive. This is just all polynomials, all of whose coefficients come out of I. So it's sum alpha I xi, alpha I is an I. Basically, this is the smallest ideal of the polynomial ring generated by the ideal I. And I power x is sort of an analog. Zero, infinity of alpha I xi, alpha I. So this is all power series, all of whose coefficients are I. A, IX, and RX is an ideal. And RX modulo IX is isomorphic to R mod I. That's convenient. This ideal is also a polynomial ring over the ring R mod I. There's an analog for power series. Morphic to R mod I. By the way, just as a passing remark, we may talk more about this later. This is the smallest ideal of Rx that contains all the elements I, right? Because if you have all the elements from the ideal I, then you can form anything like this, and anything like this is contained in here as well. This is usually bigger than the smallest ideal that contains all of I, depending on how R is. But this contains the smallest ideal that contains all of I. I X prime and Rx if and only if Ix is prime and of course that's true. If and only if I is prime. No. There's a remark in number C about respectively maximal for Rx. It may be true vacuously, but actually one of the things you prove in the homework is this thing is never a maximal ideal of Rx. The I is prime. I is prime in R if and only if I power X is prime in R power X. E prime effectively maximal in R if and only if I comma X is prime effectively maximal in Rx. And F I is prime effectively maximal in R if and only if Ix is prime maximal in R power X. So let me talk about the details of some of this anyway. So I'll do a sketch of some of this. The proofs of these are very much the same. So let's look at A. Why is this an ideal? I'll leave that as an exercise. Since I is an ideal, this thing is clearly a subgroup, is it not? Or, well, this one, I guess in this case is a subgroup because basically it's a polynomials of this. If you add two polynomials, all the coefficients are I. You take the difference of two of those and it's going to be a polynomial, all whose coefficients are I. And it's clearly a vacuum cleaner, isn't it? Because all the coefficients are sucking all the R's in. That's not too difficult. How do you show this? Well, if you look at phi from Rx into Ri mod x, I love first isomorphism theorem, and that's where I'm going with this. What I'm going to do is I'm going to take an arbitrary and I'm going to let this be a sum Rn plus I n. Or some of you, if you like this notation, might like this is Rn bar xn. So basically what you do is you reduce all the coefficients of the polynomial mod I. This is an onto homomorphism of range, right? Because clearly any Rn bar xn comes from actually many of these kind of things, right? And notice that the kernel of phi is the set of Rn xn such that Rn bar xn equals 0 bar times xn. Therefore, which is equal to the set of Rn xn such that Rn is an I. So it's Ix. So by the first isomorphism theorem, Rx modulo the kernel of that homomorphism is isomorphic to R mod I. As you might guess, the proof for the power series is almost exactly the same, right? And it's the same homomorphism where you just reduce all the coefficients mod I. That tends to be true for polynomial and power series proofs. For some of the things, the proof is almost the same, but for some of them, they're quite different. So this makes B and C pretty easy. So notice that, for example, for C, suppose Ix and Rx is prime, then Rx mod Ix, which incidentally is isomorphic to R mod Ix, is an integral domain, which implies R mod I is a domain, which implies that I in R prime. And this, of course, heavily depends on this right here. And the reverse of this proof is almost the same. If I is prime, then now power x is prime. And so if you use the isomorphism again, you get Ix prime. Let's see, we'll do a power series one. And I want to illustrate just so that we're on the same page. Let's do F. And part of my motivation for doing this is so that we make sure that we know that, what exactly I mean by this in particular. Let's see if I can get away with, doing these in tandem. Suppose I is prime or respectively maximal in R, and consider X. Now I'm going to make a little claim here. It's this part here. I'm going to make a little claim here. I claim, now notice that IX, this is actually an ideal of Rx. This is the stuff of the form alpha f of x plus x times g of x, where alpha is in I, right, and f of x, g of x are in R capital X. So basically, IX is, you can multiply, it's anything in the form I times f of x. Actually, I guess I'm really kind of, I guess I could write this a little bit more generally here. Yeah, I should write this a little bit more generally. 'Cause I don't know what the terms are. Alpha I, F I. Where alpha I is 9 and Fi. So in other words, it's the smallest ideal that contains all of I and all squared x. Now, I'm going to do something similar to what we did in part D in the following sense. Consider the homomorphism right. Next, let's do this. Let's look at this homomorphism here. I want to call it phi. And phi, this is maybe a little bit even more easier to understand. I'm going to write this typical thing as A n x n is equal to A0 plus I. So here's what this homomorphism does. It takes the power series and it freaking forgets about everything except the constant term, which it reduces mod I. That's it. So it ignores most of this power series. It just says whatever A0 is, I'm going to reduce you mod I. It is easy to see that this is a homomorphism. Because basically when you add two of the constant terms up, you get this, you break it up, it's easy to see it's a homomorphism. And it's on. Is everybody comfortable with that so far? Any worries so far? Notice that the kernel of phi, I claim that the kernel of phi is actually I comma x. Let me show this here. Suppose A0 plus A1x plus A2x squared is in kernel phi. Then A0 plus I equals 0 plus I. So A0 is in I. And this means that I can break this up as A0, which is in I, plus A1 plus A2x plus, and this is generated by x. So this is actually an element of okay with that. So if you're in the kernel, you have to be in here, and the other way is easy as well. That this way, suppose that f of x is in I comma x, and we write f of x equal to A0 plus A1x plus A2x squared, et cetera, then we should be able to decompose this into the sum of alpha I fi x plus x g of x but notice that this part right here is in the ideal generated by x. Right, and since this is an ideal, this means that A0 well, so A0 equals minus A1x minus A2x squared plus the sum of alpha I x of x. This piece is in the ideal generated by x, and A0 is in I comma x, therefore A0 must be an I. So A0 plus A1x plus A2x squared, et cetera, must be in the kernel, because the constant term must be an I. Okay, right. So there's my claim that the kernel is precisely I comma x. So R power x by the kernel is isomorphic to R mod I. And now that we've got this, that's the death grip right there. Because if I is prime, well, let me instead of doing it this way, so I and R is prime, respectively maximum, if and only if R mod I is a domain, respectively a field, if and only if mod IX is a domain, because those two are isomorphic. If and only if IX and our power X the prime. And there you go. Any questions on that? Let me give you a corollary. This is something that is absolute. You actually in your last homework, I think your last homework, or maybe it was this one. I don't remember. One of these homeworks, you showed some stuff about. No, it is the last one. You show that any commutative ring, if you have any commutative ring with identity R, then the polynomial ring has infinitely many maximal ideals. This is very different. Corollary 5, 6, 7. R be commutative with identity. Maximal ideal of R power X is of form M comma X with M and R minus. This is not true for polynomial rings. For polynomial rings, these are all maximal ideals. It is true, but polynomial rings have many, many more. Power series rings, all of the maximal ideals are this form, and that is incredibly, it's actually one of the very rare instances where power series actually behave in a nicer fashion than polynomials do. In particular, R is quasi-local is an only Rx or power X is semi. Let me outline this really quickly. Proof. We know that Mx is maximum. Period. Right? In fact, this is true for polynomials and power series. These are maximal. And this follows from what we just did. Part F, I guess it is. On the other hand, gamma in R power X is maximum. We claim that X is, this is not necessarily true for polynomials, and this is where there's a big difference. Why is it the case that X is in gamma? Well, if not, consider, well, in fact, we don't even have to say if not, we'll consider the ideal X. Right? Consider that ideal. Now, note that if X is not in gamma comma X, then gamma comma X strictly contains gamma, and so gamma comma X will 1 or equal to R. So there exists gamma X, gamma, and f of X in our power X with gamma X plus X f of X equals 1.
Why is it not X not in
X. You're right. If X is not gamma. Now take this equation and plug in X equals 0. And I get gamma of 0 equals 1. So gamma X is then u bar power X, which is the conjugation. And so I will, since it's time out and time for Thanksgiving, I'll leave you to figure this out, but we can go over it a little bit. Now that we have that X is in gamma, then we're good to go, because from here, what you need to do is now look at ideal. Zero, which is a set of F of 0, set gamma of 0 or gamma. And show must be matched there. And you're done then. So anyway, see if you can puzzle that out. And if not, we will power through it after Thanksgiving. Any questions? Any questions? Okay, y'all have a happy Thanksgiving, and we will see you when we get back.
Have a nice Thanksgiving.